All right, welcome everybody. Today we're going to do projectile motion crash course. I'm going to do a nice example for you, and then I'll give you a problem to solve. Okay, what do we need to know in order to do projectile motion? We need to know how to use vectors. We need the definitions of velocity and acceleration, and we need basic kinematics equations. So the most important thing about projectile motion is that we can consider the x and y directions of motion completely independently. What's happening in the x direction has absolutely no bearing on what's happening in the y direction. So we need to split up the motion into x and y components, and then we can solve for the quantities that we want to know. So this is a classic projectile motion example. A ball is launched off a cliff of height 34 meters horizontally with 15 meters per second in the x direction. What time will the ball hit the ground, and how far away from the cliff will it be? So the first thing we're going to do is we're going to make a table, and we're going to list different x and y values. So let's start with the x. Let's make our coordinate system like this. We have 0 here, and this is the positive x, and this is the positive y. So our x initial position, since we are starting up here at the top, our x initial position is going to be 0. Our x final position, somewhere down here, we don't know where that is yet, so we're going to leave that as an unknown. Our velocity in the x direction initial is also an unknown quantity. That's not provided for us. And the acceleration in the x direction. This is a very important distinction for projectile motion. We are launching the ball off of a cliff in the horizontal direction. That means that when we launch it, if there was no force due to gravity to pull it down, we would simply continue on in this direction. Another way we can think about it is let's draw a free body diagram for this ball in, let's say, this position. So in the middle of its trajectory. And we'll start with our point-like mass. And so now for free body diagrams, we have to think about forces. And we have to use object egoism. Me, right now. What's happening to me in this very moment? So we know, because we're dealing with Earth, that we are experiencing the force due to gravity. And then in general for these, we're going to be working in our fun physics land of a frictionless vacuum. So there's no air resistance, so we don't have any force in the upward direction. And similarly, we have no air resistance in the x direction in either direction, positive or negative. And so let's become the ball and let's think about what's happening. Is there any other force that's acting on the ball in the positive or negative x direction? And there is not. We're not pushing the ball as it's falling through the air. We just have the force of gravity. So, using Newton's second law, force is equal to mass times acceleration. If force is 0, then acceleration has to be 0. So if there are no forces in the x direction, the acceleration in the x direction has to also be 0. And that is the key thing to know about projectile motion, is that if nothing is given as a force in the x direction, there's no acceleration in the x direction. The time that it takes is unknown. All right, now let's move over to the y direction. Our y initial position at the top here is the height of the cliff, 34 meters. Our y final position, we are going to hit the ground. That means our final y position is 0 meters. And our velocity initial in the y direction, let's think about it. So right off of the edge of the cliff as soon as it is launched off. What's the motion in the y direction? Well, we know that we have a velocity, 15 meters per second in the x direction. But in that instant, right before it starts falling, it has no velocity in the y direction. It has not started accelerating due to gravity. So the velocity in the y direction initially is 0 meters per second. The final velocity in the y direction is unknown. How about the acceleration in the y direction? Well, we just saw in our free body diagram that we had the force of gravity, and we know that the acceleration due to gravity is g, which is negative 10 meters per second squared. We have to make sure that we use the negative acceleration because it's in the negative y direction. So we're going to use negative 10 meters per second squared. The time that it takes at this moment in time is also unknown. We don't know how long it's going to take to fall. However, what we do know is that these two times are the same. It seems kind of obvious, but it takes the same amount of time to hit the ground in the x direction as it does in the y direction. You hit the ground at the same time. It's one motion. It's one curved path. So there's only one time that it takes to get from our initial position up here to our final position down here. Okay. So let's use one of our projectile motion, our kinematics equations. The most useful one for us is going to be the one that includes acceleration, position, and velocity. So let's do it in the y direction. Y final is equal to y initial plus velocity initial times time plus 1/2 acceleration time squared. Let's use the y quantities. So that means that the final y position is 0. The initial y position is 34 meters. The initial velocity is 0. And the acceleration is negative 10 meters per second squared. 0 times time is always 0. Let's subtract over 34 from both sides. And then we'll bring it over here. So we have negative 34 equals negative 5 t squared. Divide by negative 5. Divide by negative 5. T squared is 34 divided by 5, which is 6.8. And you need to take the square root of that to get the time. And that will come out to be, if my calculator will work. Come on, calculator. Oh, don't do this to me. Oh, you gotta be joking. Well, square root of 6.8. Which, come on. All right. Is 2.6-ish, approximately, seconds. So the time is 2.6 seconds. Well, that gets us somewhere. What we really need to know, though, so we said what time will the ball hit the ground? And that's what we just found here. How far away from the cliff will it be? That's the next question. So this is actually a lot simpler of a question than the first one. You might think that you need to use some kinematics equations, and you could if you wanted to, but it's a lot easier than that. So we know that for a constant acceleration or a constant velocity, we can use the definition of velocity, which is change in position over time. If we want to find the position, we can rearrange this right here, and we get velocity multiplied by time is the position. So we have 15 meters per second in the x direction, which was given, oh, I made a mistake. Our v, that should not be vx, and it should be v, should not be a question mark, that should be 15, as it was stated previously. So we have 15 meters per second multiplied by time, and that gives us our distance, which is 39.11 meters. 39.11 meters. And that's it. We have used projectile motion. We've used the kinematics equations. We've listed our different values in the x and y direction. And we've used our knowledge that whatever happens in the x direction has nothing to do with what happens in the y direction and vice versa. And we found the distance that it takes to get the distance that we travel in our projectile. So here is a problem for you to try. So we have what essentially amounts to a conservation of energy problem. And a projectile motion problem. So you can use conservation of energy to find the velocity that it leaves the table. And then using the velocity that it leaves the table and the amount of time that it takes to fall, you can find this distance. So I hope that was useful. If you need more help, come see me, and thanks for watching.